Welcome to solverfy.
I quite enjoy these practical questions like number 56, where we want to know the pressure on a solar sail that's around the distance of Earth, and then calculate the acceleration on that solar sail, and then finally how big of a sail you'll need to accelerate a payload at a given acceleration. So for part A, we can get the radiation pressure, which is given in equation 22-10b, and it is equal to 2 times the average intensity divided by the speed of light. And we have the average intensity over here. It was given to us in the problem, and it is equal to 9.00 times 10 to the minus 6 Newton meter squared. And that is a pressure, which is a force per unit area. So then we can use Newton's second law to calculate the acceleration. So if P is force per unit area and force is mass times acceleration, we can solve for acceleration. Red seems to be appropriate here. And it is going to be, what is that? PA over M. And what we have is that the mass is 1 gram per meter squared. So it's probably better to write this as P over mass over area, because mass over area is the what's given in the problem prompt. So then we can plug in for what we have, and we get that the acceleration is roughly going to be 9 times 10 to the minus 3 meters per second squared, which is interesting. It's not really going to be 100% accurate, though, because there's obviously gravitational attraction due to the sun's mass. And that might change the acceleration here. It's hard to say. You'd have to do a full analysis, but that's beyond the scope of this question. And then finally, for part C, we have that we want to put a payload on this and accelerate it, and we want to accelerate a 100 kilogram mass at about 1 times 10 to the minus 3 meters per second squared. And what we can do there is figure out the required force. But that is going to be of the total mass, which is the payload. So we'll say mass P for payload. We'll say MT is mass payload plus the mass of the sail itself. So we have to consider that. And if we go to our equation that we have here, we basically want to rearrange our area, or rearrange to get area, which is just MA over P. But again, that is M payload plus M sail over the pressure. And the mass of the sail has a kind of a complicated, it complicates things, if only because it changes with the area. So we have something that depends on what we're trying to calculate. So that's 0.001 kilograms per meter squared times the area itself. But it's not the end of the world, because we can separate things out ever so slightly and divide on both sides by that, I'll write it again, leading to the area being the mass of the payload times the acceleration divided by the pressure minus the density of say 001, the density of the solar sail times acceleration again, which is what we already have. And finally, by calculating all of this, you get that you will need a solar sail that has an area of 1.25 times 10 to the 4 meters per sec, or no, meters per second, just meters squared. So that is quite a large sail. We're talking, like 100 meters on both sides. So that's something you certainly have to unfurl once you get to space. But again, this can't be considered 100% accurate for the same reasons I mentioned in part B, where the sun's gravitational pull on our equipment is going to have an effect.